ecological engineering at Oregon State University. His expertise is in spatial simulation of environmental and agricultural systems. He has a PhD from Auburn University in agricultural engineering a few years ago, not too many. And his specialty is in the analysis of alternative futures. But I thought, well, is that like alternate realities? So I guess we're going to find out a little bit about the kinds of realities that John and his colleagues are focused on. So please give a warm science pub welcome to John Bolte.
Is the mic on? And can people hear me okay? Does this sound about right? Good back there? Okay, sounds good. We'll assume that goes. And if for some reason people have a hard time hearing, don't hesitate to jump up and let us know. We'll adjust the sound accordingly. So first of all, thanks for the opportunity to be here tonight. I'm really impressed with the crowd. And when we talk about 50 years from now and there's twice as many people in the Willamette, you're going to have to get a bigger venue. It's just not going to work packing too many more people in here. But that also raises a really interesting question about as growth happens, and it's you can argue, I suppose, whether it's inevitable or not, but the projections are all pretty clear. There's going to be a lot more people showing up in the Willamette Valley here over the next 20, 30, 40, 50 years. And one of the big challenges is where do these people go in ways that accommodate the needs around growth, but also take into account the fact that we care about our ecosystems, we care about the services that ecosystems are providing for us, we care about having access to the river, we care about all these amenities that is one of the reasons a lot of us are living here in the Willamette Valley, and it's a real challenge. And one of the things we try hard to do is to anticipate some of the challenges that will be coming out of this growth experience, and trying to plan for those in some sort of way that anticipates change, understands some of the consequences of some of the choices we make about how we manage ourselves as a society in the Willamette Valley, et cetera. So that's really a nice segue into the talk tonight. What prompted this talk is a proposal and a project that was funded by NSF last year, a 5-year project. I'm going to talk more about the details of that project in a little bit, but I just want to say one thing up front about the project. One of the challenges that face the scientific community when we start to look at things like the Willamette Valley, that is fundamentally a very complex system. There's lots of stuff going on here. Even when you focus your attention on water, you can't really talk about water without talking about growth. You can't talk about water without talking about agricultural, natural resource industries that are water users and potentially have quite a bit to say about how water works in the valley. You can't talk about water without talking about fish and endangered species, et cetera, et cetera. One of the statistics and the trivia question about salmon runs is a really good example of that. So all this stuff is tied together. And one of the real challenges from a science point of view is, as scientists, we're much more typically trained to focus on, break problems down, focus on little pieces, and we often neglect the fact that these little pieces are part of larger systems. And so one of the reasons we were successful in this project was through recognition, and OSU is really good at this, that it's not about just the pieces, it's also about how all these pieces fit together. And so when I start to talk about the specifics of this project, it'll be within that context of how do we begin to assemble descriptions of change in these systems that represent significant portions of the complexity of those systems, and then play those out so that we have some sort of sense of what we can expect in the future under different assumptions about how we manage ourselves. So that's sort of the big picture version of the talk. I think I probably went through this enough. You are here. You are about right there. But just so you have a sense, my guess is everybody has a sense of the geography here a little bit. But that's sort of a big picture view. I'm going to talk a little bit about history as well. There's a long history of interest in water in Oregon. I don't know if you can read this or not, but it says demand clean rivers, and there was a period of time when the Willamette was in the national news as a good example of how not to manage a river with pollutants of all sorts spread throughout the river, et cetera. Those go back to the 60s and 70s. And not only did we have a reputation of having a bad river, but the response really provided Oregon with a reputation for caring about the environment, for taking care of their waterways, et cetera. There was a huge cleanup effort that was by and large very successful, particularly by the standards of the time. But the sort of the history of interest in water in the Willamette goes way back. This is from Portland. The usage, the human usage of the Willamette River in particular goes way back as well. One of the questions was about steamboats and steamboat traffic in the Willamette. This is a photo from the 1870s that shows a good example of that. This is on the Willamette River, one of the steamboats. There's lots of very cool historic photos of steamboats if you're really interested, but it was used for commerce, it was used for transporting people, and that was a very active part of the use of the river, going back to really the 1860s. The Mackenzie River, this is a more recent example of another type of usage, in this case recreational uses that are focused on fishing in this case. Yet another example of what we refer to collectively as stuff people care about in the river. This is an example of that. And that carries through to the modern day as well. This is a picture that was taken from one of the Riverkeeper trips, I believe. Recreational use has always been important, but also uses for commerce have been historically important as well. So lots of interest in the Willamette. You know, the turnout here tonight is I think a good example of that. This is, and I hope you can read this. I'll try to just concentrate on some of the details here. This is a depiction of the river, cross sections of the river, starting with Portland in this area, upper left-hand corner of the screen, going and then down to Eugene, Springfield, and showing the historic floodplain that was associated with the river in 1850. Quite large, and these slices down here, this bar graph down here, describes how long the river channel was in each one of these little slices of the river. So how long the river channel was translates into how complex was that channel. Was it a multi-channel meandering panel, or was it meandering channel, or was it a straight path? And typically, from a ecosystem health point of view, we like to see large numbers on that. That indicates that the stream is doing its work, it's providing lots of habitat, and generally doing the things that rivers do quite well. And then as you go downstream to Portland, the river gets simpler and simpler until finally you get out to the point where there's not a whole lot of meandering channels, et cetera. But particularly in the upper watershed up here, that complexity of the channels turns out to be really important ecologically. This is what it looks like now. We've done a lot of improvements to the river. Many of those improvements involve straightening channels, involves putting in revetment, all for good reasons, mostly related to protection of property and resources. But one of the side effects of that, or one of the consequences of that, is that we've lost a whole lot of complexity in the river channel through time, and so we've lost a lot of the ecological function that goes along with that complexity in the system as well. All this, we're going to talk about trade-offs quite a bit tonight. This is a good example of a trade-off. We improved the navigability of the river. We improved the protection of property around the river, but we gave up a lot of ecological services as a result of some of those modifications. The Willamette does lots of things. One of the things it does is flood. I don't know how many people were here in 1964. Very many of you? Okay, so you probably remember this. It's a place that's susceptible to floods. This is downtown Corvallis. 1964, 1943. Here's what Corvallis looked like at one point in the winter of 1943. This is looking from Albany towards Corvallis. Another big flood, and you'll notice significant chunks of the landscape are underwater here. Salem, 1890. Another flood. Well, the picture speaks for itself. I won't say anything more about that one, other than to emphasize that one of the things rivers do, and the Willamette is pretty good at, is flooding. I'm going to talk a little bit about scarcity in a little bit, and a lot of people might say, well, he's talking about water, he's talking about scarcity. I don't see a lot of scarcity here, but the fact of the matter is there is scarcity represented in these depictions. It's scarcity of protection from floods. So there's lots of different ways to think about scarcity, and I bring that up now because I'm going to touch on that a couple more times as we go through here. Lots of ways to define scarcity. For some of you short timers here, going back to 1996, and I can say I was here in 1996. I wasn't here in 1964, but I was in 1996. Many of you probably remember the 1996 flood. This is when, after all the core reservoirs are in and all the flood control is in, and even that, the Willamette still floods. And this wasn't even a particularly large flood by Willamette standards. So this is one of the things that interests us about this river is not only the bad things that floods do, but potentially floods do some good things as well. But we also need to keep in mind that as we think about the human footprint on the landscape around this river, this is one of the facts of life that we have to pay attention to. To give you a little bit of sense, I talked previously about the loss of complexity in the floodplain channel. This is a good example of that. This is a figure from Dogami, actually, Department of Geology and Mineral Industries, that reconstructs. You can see Corvallis right up here. This is the Willamette River, obviously, and the current channel. And you hopefully can get a sense, looking at some of these enhanced imageries that were done with a technique called LiDAR, I'm not going to get into, that really reveal the historic channels or channels that were associated with the Willamette in this stretch of the river. This is a really good example where we used to have a very large floodplain. It used to be quite complex, lots of meandering channels. These are really good places to do things like grow Chinook salmon, the fingerling Chinook salmon, provide habitat for a whole range of species. Most of that's gone at this point. So as we think about the Willamette, one of the things, if we're interested in restoring ecological function, that 1% of historic salmon runs is a pretty startling statistic if you haven't seen that before. This is one of the things we talk about is how do we begin to reconnect the river to its historic channels so that we can begin to recover some of that complexity in the river system that is good for doing certain types of things. It's good for doing things like rearing fish. It's good for doing things like absorbing energy associated with floods, but it's also bad at doing things like staying in a particular place. Got me. I couldn't tell you. Anybody else? I believe, and I'm not certain of this, I believe this is a view looking south, sort of from Albany towards Corvallis. Okay, does that get you oriented? Okay, sounds good. Sounds good. Okay, other things we do to rivers in Oregon, and we're certainly not unique in this regard, is put in things like dams. Dams are really important for obvious reasons. They're really important for flood control. They're really important for storing water for uses during periods when there isn't so much water. More on that in a little bit. They're useful for recreation, but they have issues as well. Particularly some of the early dams were not really designed with fish passage in mind, so they became very heavier barriers to fish passage. They're also doing things like accumulating sediments and changing downstream temperature regimes and a bunch of other things that are maybe not necessarily good things. But again, we're in this sort of realm of trade-offs of there are things we can do that have both good effects and bad effects depending on your perspective. And that's one of the facts of life here. These dams are really important because when we think about how can we change the flow regime in the Willamette, and a lot of things really come down to what's the flow regime look like at key times of the year. These dams are the big levers that we have in the system to actually control that. We can do a lot of really interesting things with dams, like take water from the surface as well as at the bottom, warmer water on the surface, colder water on the bottom, mix those in certain ways that we get the right temperature coming out of the bottom of this to support things like endangered species, salmonids in particular. So they become potentially quite useful tools for, you may hear me refer to dials and knobs, turning dials and knobs in the system that allow us to tweak it in this way or that way. Dams are really important because they're the big by far, the big knobs in the system that we have some control over. To do things like modify flow regimes or modify temperature regimes associated with those flows. et cetera, et cetera. Dams are sort of interesting. It's a real mix in the Willamette Valley. This is within the Willamette River Basin. We think of the federal dams. All of us are probably familiar with the federal dams. I would guess probably a lot of us have recreated behind those dams at various times in our lives. They're pretty big. This is the catchment area, impoundment area, and amount of storage. This one's probably the most important one to focus on, the amount of storage. We can store a lot of water behind those federal reservoirs. But they're not the only part of the picture. There's a bunch of other things going on here as well. The state manages a bunch of dams. Local utilities, municipalities manage dams. Utilities manage dams, and there's a bunch of private dams. Tend to be smaller in scope than the federal reservoirs, but they're still a significant part of the pictures. When you look at all of these dams across the Willamette Valley, I'm not sure what the exact numbers is, but it's in the several hundred important dams, and then a bunch more little tiny ones that we don't really even track. What the dams are used for is also, I think, a useful thing to think about. Most dams are used to provide irrigation water. That's the primary use of dams in the system. One of the trivia questions was, which uses more water, domestic or ag? And just out of curiosity, how many people said ag on that? And how many people said domestic? That's not too bad. You'll see how you did against some other folks in just a little bit here. But irrigation is a big reason why those dams are there. But there's some really interesting institutional constraints on how this water behind dams gets used, particularly if you're talking about non-irrigated purposes. It basically can't be used for non-irrigated purposes. And there's lots of other things that go on. A fair amount of hydroelectric generation. Quite a bit is used for recreational purposes, and some of these dams serve multiple purposes, so they get counted multiple times here. But irrigation is really the big use. I got to point out the beaver here. Reason we call this the beaver state is lots of dams. Okay, that was my subtle attempt at humor. We'll leave that at that. So what else is going on in the valley? Well, there's a whole bunch of things. I'm just going to touch on a couple things. Population growth is obviously important. We've seen this trajectory since European settlement. We're sitting right here around 2.5 million residents in the Willamette Valley. What's going to happen in the future? Well, who knows? But the best estimates are that we're going to basically get up to about 5 million over about 50 years. You look 56 years out, you're really looking at just about a doubling of the population. And that assumes lots of things, obviously. It assumes, current trends sort of continue on out. But what it doesn't include is things like climate refugees. That one of the interesting things about Oregon, when you look at it from a climate perspective, is it's relatively unimpacted by projected climate change. That's very different than places like Arizona and Southern California that, if you believe the projections, there's going to be pretty tough places to live for lots of reasons. But this number could easily get pushed up just through this climate refugee thing, perhaps or perhaps not. Who knows? It does. Yeah. So the question was, does the Willamette Valley include Portland metro area? And the answer is yes, for the most part. Not completely, but for the most part, Portland is included in that 2.5 million number. And obviously, that's where most of the people are. Okay, so that's one kind of stressor. The other thing that's going to be going on with population is it's quite likely that most of those people are going to end up in cities. But again, this is something that is our best guess and may play out differently depending on things like land use planning laws. As most people in the room are familiar, we have a pretty rich tradition of land use planning in the state. Some people love it, some people hate it, but it's there. And one of the things it has done is tends to put more people in cities than it does in rural landscapes. That's one of the intents of the land use planning system, is to protect those rural landscapes for resource use. So depending on what happens with our land use planning system, this maybe goes up or maybe this goes down, or it's one of these examples of a dial in the system that we have some control over. Not complete control over, but we have some control over as a society. Wait, wrong way, sorry. So I want to talk a little bit about water consumption. And this is sort of, okay, so where's all this water go? We think of Oregon as being a water-rich place, and that's true in some ways. It's untrue in other ways. But where does it go? And in Oregon, in the Willamette Valley at least, about half goes to agriculture. Across Oregon as a whole, that number is 80%. But in the Willamette Valley, where we have more people and less agriculture compared to the state as a whole, you think of Central and Eastern Oregon as primarily ag-dominated areas. Within the Willamette only, about half of the water consumed goes to agriculture. 20% commercial, 13% industrial, and only about 15% domestic. For the state as a whole, the numbers shift quite a bit. Again, agriculture becomes much more dominant when you look across the state. And then the rest sort of gets parsed between relatively small contributions. I put this up, first of all, because it's interesting just to get your head wrapped around. The second thing I would say about this is when we start looking at ways to manage water in the future, if we want to talk about conservation strategies as part of the mix of strategies that we want to look at, then obviously we'd want to look at conservation strategies for ag as well as everything else, but we really can't ignore this and focus solely on any of these other ones, or we miss a pretty good chunk of the business, of the picture. Let's see, I think that's probably, well, I'll say one more thing about this slide. In presentations like this, you got to look at these a little carefully because nothing is simple. One of the things about agriculture is that it's consuming a lot of water, but it's also recycling a fair amount of that water. You put water on a crop, some of it gets taken up and lost through evapotranspiration. Some of it goes down in the soils and will eventually return back to the system. So interpret all these numbers with a little bit of caution because there's complexities in here that depending on what you account for and what you don't account for, may skew the interpretation a little bit one way or the other. That's all water use. I believe so. I don't have the surface water to groundwater split on the top of my head, but that'd be a good thing to look at. I put this up because there was a study that Brent Steele at OSU did a couple years ago that asked people, where do you think water is being used? And you guys did pretty well. Most of the crowd voted for ag on this one as opposed to domestic. But it's surprising how people's perceptions can be different. This is in metro versus non-metro areas. Metro are any locations that have cities more than 50,000 people. So Corvallis just crosses the threshold. Non-metro is every place else that isn't a city with at least 50,000 people. Some difference, although not as much as you might expect. But in all cases, the perceptions at least were that municipal uses are the dominant water use in Oregon, and ag is close but somewhat behind. And these other ones are almost noise at this point. But the point here is that people's perceptions in reality don't often align, particularly around water, because water is sort of this funny thing that's just assumed to be there. You turn your tap on and water comes out. You go down and walk down First Street and the Willamette is sitting there running. We tend to not really associate values or uses with that water quite so directly, and so that results in sometimes these sort of skewed perceptions on where water actually gets used compared to where people's perceptions on that are. One of the reasons I put this up is when we think about this project that is sort of the reason for this talk, one of the things we're trying to capture is not only the science realities, but also people's attitudes and behaviors and incorporate that into our analysis. I'll talk a little bit more about that in just a bit. Water everywhere is the title on this slide. A lot of people think of the Willamette as a pretty wet place. And it is a reasonably wet place. You look at precipitation numbers, and particularly as you get up into the foothills and the Cascades, they tend to be a fair amount of water coming in here. But that said, lots of water falling, but there's also a lot of water being consumed in the system here as well. This is a figure that depicts in spatial form, so this is the Willamette Valley, where there's available water rights. This was a few years back. I think a couple of these ones may have dropped off the map at this point. Surface water rights in the Willamette are getting very limited. If you've got access to the main stem of the Willamette, you have access to water rights. But as soon as you get off the main stem of the Willamette, there's no more water rights available. And I'm not going to say a whole lot about water rights. I guess as most people in the room have at least some sense of what water rights are about. But if I'm up here and I say I want to get a new surface water right in the Sandian Basin, let's say, and I go to the Department of Water Resources and say, can I have a surface water right? They're going to say, no, probably not, unless there's some special circumstance because the water's all been allocated already. It's referring to surface water rights off any surface water source in the Willamette Valley. So the water behind the reservoirs is part of that if you are directly downstream of one of the reservoirs, and that's pretty much the main stem. And meaning those rights exist. As soon as you get off, if you can't stick a straw into the Willamette, you're pretty much out of luck when it comes to available water rights. Things really are pretty scarce here, and this isn't OWRD gone wild. This is actual, when's water available, and a lot of this comes down to timing. Most of this water, as everybody knows, except for this year, falls during wintertime, whereas most of the demand is late summer, when most of that wintertime water is either stored behind dams or it's gone downstream already. I'm going to talk a little bit about climate. I'm not going to talk much about climate because I'm not a climatologist, and there are people in this room who know more about this than I do. But I like this slide. The picture is pretty bleak, ladies and gentlemen. The world's climates are changing. The mammals are taking over, and we all have a brain about the size of the walnut. This is how I feel many mornings when I walk into my office. Is and I'm not going to argue with anybody about climate change. I mean, it's happening. There's very little question about that from the scientific community. The question is, do we know enough to do anything about it, and how do we even get our heads wrapped around that? And so that was a big driver for this proposal that we put together. Project was trying to get at just that question. We have a pretty darn good sense that climate is changing. We even have a pretty good sense of sort of the particulars of that, the wheres and the hows, and the amounts of that at this point. We don't know that with super certainty, but we're getting more and more confident all the time, and the numbers seem to be tracking the predictions quite well. In fact, if anything, we're underestimating change with the models. But we're just starting to get our heads wrapped around of, okay, so what do we do about this? What are the consequences, and B, what can we do, if anything, at this point to begin to mitigate that? And again, I'm not going to say very much about climate because I'm not a climate scientist, and I recognize at least 3 people in the room who know more about this than I do. But just to sort of set the stage a little bit, we're talking about long time ranges here, and I put this slide up, and not to argue over the particular columns, but to make the point that as we see increases in emissions of CO2 and other greenhouse gases, coming out of our activities, they have an effect, and we're seeing those effects now. It's the evidence is pretty overwhelming at this point. But the real consequences are that even if we get our emissions under control here pretty darn quick, it doesn't make much difference because we set things in motion that result in these sort of long-term changes that we're going to have to plan for. And so this is really an adaptation process that we're in, of which we know we have very little experience with. We haven't experienced planets that have CO2 levels that are double historic conditions, for example. And so we're not quite sure what's going to happen, but nonetheless, we got to figure out how to plan for that, not necessarily being certain what's going to happen. So that's one important driver in the system. In terms of predictions for the Willamette Valley, and here I'm going to focus on the lower Willamette Valley, and again, without getting too bogged down in the details here, there's very smart people running very sophisticated models of climate around here, and the group at OSU is one of them, that capture a lot of the physics around climate and do these long-term projections of change. There's a handful of these models that are sort of widely accepted. They've gone through peer review and all the things we as scientists sort of count on to verify and validate work. This is one particular model called the Hadley model. There's other models, so you're getting a relatively small picture of the whole here. But just to give you a little bit of sense of what one of these models predicts, this is temperature change under what's called a B1 scenario, and B1 is a very green scenario. It's okay, let's get serious about mitigating emissions. Let's get serious about carbon capture technologies, and let's really do the stuff we need to do to aggressively approach climate change. So this is a very optimistic scenario. Well, even under the most optimistic scenarios, we get pretty significant changes in temperature, particularly late summer, when is where the demand for water is the highest. Again, the models vary, and I would take all of them with a little bit of a grain of salt, but they're talking about a minimum of about 4 degrees and a maximum of about 12 to 15 degrees change under an optimistic scenario for late summer average temperatures. When we go to an A1B, which is a sort of business as usual scenario, we sort of maintain emissions at their current levels without being too aggressive about reducing those, and see what happens. The numbers get worse, and we get up, numbers that are in the range of 12 to 15 degrees change in temperatures over late summer. So pretty substantial impacts, particularly when you start to look at water use that goes along with these levels of temperature change under a sort of status quo scenario. And there are, these are not worst case scenarios. These are sort of status quo scenarios. But when we've tracked, when the climate scientists track the results of these models compared to what they're actually observing on the ground, it turns out that even in this period where we've had this sort of declining economic situation that has a very substantial increase in emissions that go along with that, because emissions are tied to economic development quite closely, we're doing much worse than this. Well, much worse is not a fair statement. We're doing worse than the status quo scenario when we look at actual observations on the ground compared to what the models are predicting. So all these ones could be off. They're for sure off, but the bounds are probably pretty close. If anything, they might be a little bit conservative. It's a little hard to say, and again, I'm getting out of my domain of expertise here pretty quickly, so I won't say much more about that. So here's an example of a side effect. A side effect of increasing temperatures, and that is snowpack. So this is based on some work that Hee-Jung Chen at Portland State did. He's one of the collaborators on this project. As well, this what we refer to as Willamette Water 2100 project. Really good scientist. I'm really impressed with Hee-Jung. He's very careful in his work. They've been modeling impacts of climate change under these different climate scenarios and different model predictions of change for Oregon, and mapping those into changes in snowpack, and pretty substantial differences. Basically, blue here is lots of snow. As we go out to 2040, 2080, this disappearing blue, if you believe this, and I encourage everybody to view all this stuff pretty skeptically, but if you believe this, we've got some real issues around snowpack. And in fact, by the end of next century, the expectation is that snowpack will be reduced by at least 80% compared to current conditions. So what are the side effects of that? Well, when we talk about late summer water, which is again that really important period where crops need water, people need water, fish need water, etc. The reason we do as well as we do today is because that snowpack holds up that rain and stores it, basically. And as it melts throughout the summer from the upper Cascades, these are all pretty high elevations, a lot of the snow may not melt until June, July, August, and feed that system down below. As we lose that snowpack and replace it with rain that doesn't have that same persistent storage on the landscape, we get a bunch of consequences, none of which are good. We get flashier landscapes that are more flood prone. We saw those floods before. We've got dams in place right now that hold the 10% was optimistic on that trivia question. It's really closer to about 6% of the annual runoff in the Willamette Basin can be stored behind the dam, so it's a pretty small number. It's tough to build new dams because they're very expensive, and there's a whole bunch of other sort of side effects associated with dams. But what I hope this demonstrates is storage in the landscape is good. Snow is nice because it's free. It doesn't cost anything to build snow. Nature does that for us. It's a good example of an ecosystem service. But as we look at warmer and warmer temperatures, we lose that ability for the landscape to store a lot of that water resource. That's a really good question. I don't know the answer to that. I'll hazard a guess, but I would also encourage anybody else in the room who is knowledgeable on this to chime in here as well. If I had to guess, I'd guess they store about 30 or 40% of snowpack, but I don't know that for a fact. No. The stuff we've looked at so far was based on analyses that have been done in the last really 10 to 15 years, not looking ahead. But let's come back to that point in a little bit, because one of the things that we want to transition to here pretty quickly is, okay, so all this stuff is happening, what can we do about it? And messing with the dams in various ways is one way to get there. Okay, so I just want to have a slide that summarizes this stuff a little bit. Even in the short term, in the next 10 years, we anticipate significant effects of climate. When you start bumping this out, the numbers basically go up, with again, uncertainty associated with all this. Precipitation, we talked about changes in snowpack, but in fact, the total amount of precipitation is more or less the same. The models anticipate more or less about the same amount of precipitation falling in the Willamette. The big difference is that a lot more of it comes down as rain, a lot less of it comes down as snow. But at least if you believe the climate models, there won't be massive drought or massive infusions of new water into the system under future climate. And as we said, the big effect of that is reduced storage, so we get higher spring flows, which is when we tend to be more flood prone, as well as reduced low summer flows, which is where the fish really start to get stressed. So this sort of gets us on both ends. Yeah, I think we covered all that. Okay, so I'm going to shift a little bit now. I'm going to talk a little bit about, okay, so how do we understand this system? How do we explore this system? How do we assess different types of human interventions in the system that might be able to relieve stress on the system, to more cleverly allocate water, to have improved management of the dams, look at other sort of structural modifications at which we can mitigate some of these effects. And so that's what I'm going to talk about for the remainder of the talk. And we do this through this mechanism we refer to as alternative futuring, or developing alternative futures models. And this is sort of interesting. The basic idea here is we want to be able to model the system with realistic models that are grounded in best available science. That's sort of condition number one. Condition number two is we want those models to be very integrative, meaning we don't do the usual science thing of looking at one slice of reality. We try to really look at a whole bunch of different slices of reality that are all interconnected and really begin to understand those connections and relationship between components in the system and take that into account as we're looking at future change. The other thing we try to do with these efforts is incorporate stakeholder input into the process. This is, again, something that a lot of scientists, this is sort of not what we think of ourselves as doing. in a lot of cases at least. And so this idea of stakeholder-driven science is pretty front and center in this project. This particular effort is being led by Sam Chan, who some of you probably know. But one of the things we try to do is work with stakeholders to understand sort of what are the range of possibilities, the knobs and dials in the system that we want to be able to play around with to help inform decision-making from those stakeholders, whether they're individuals, landowners in the valley, or agency folks, or regulators, or water managers, or whatever the case might be. Really engage them in the process of developing these future scenarios. And then we spend lots of time on visualization and stuff like that. But the real goal of all this is really to use this idea of a scenario to play out the future. You can almost think of this as SimCity, but SimCity with real models of growth, and real models of land use, and real models of hydrology and fish, etc. But that's the basic idea. Assemble these models, do that in a framework that allows us to play out different policy constructs or decision choices, and assess how the landscape trajectories do at doing the stuff we care about, like producing fish, or producing residential housing, or producing jobs, or producing agricultural goods, or whatever the case might be. So there was an example of this that I'm going to refer to, because a lot of the work we're doing now builds on this as an example. So back in the 1990s, a group of folks from OSU, U of O, and a whole bunch of other people around the edges did an alternative futures analysis for the Willamette Valley. This was sort of interesting because it was arguably, and I don't think too many people will argue this, the best of these that had ever been done any place on the planet in the past. It was quite detailed, quite comprehensive, with the exception of it didn't look at future climate, because in the 90s that wasn't quite such a pressing issue. It also didn't look very closely at water. It looked a little bit at water, but not very much detail. But nonetheless, it was a really good example of an alternative futures project. It was led by Dave Holst and Stan Gregory, who many of you in the room may be familiar with. My group was actually involved in that, as were several other people I see around the room here today. And the basic idea of it, I use it as a good example of what an alternative futures effort is all about, because it was a pretty good example, still is a pretty good example. And the basic idea is map the place that you're studying under current conditions. So this is circa 1990, because this was a project that was done in the 90s. But map that at whatever level of detail is appropriate. In this case, we're looking at a map of land use, land cover. I won't get into the details of this. And then look at projecting that landscape forward through time by modeling change processes, working with stakeholders to identify sort of the sideboards of what possible change is. Do you look at a compact urban pattern versus a relaxed land use planning system? Well, so one of those decisions takes you this way, the other decision takes you this way. Now that's one example of a whole bunch of pieces that go into these scenario articulations, but the basic idea in this effort was to think, if we really wanted to manage the landscape for conservation purposes, what would be the decisions, the policies, the regulatory frameworks, et cetera, that we might do that, and does it actually get you there? And if it does, how do you measure the outcome? Versus, let's say, a set of policies that are more focused on letting the market drive land use, relaxing Oregon's land use planning system, and a whole bunch of other things associated with a more free market-oriented approach to future change, versus what we refer to as a planned trend scenario, which is, if you sort of keep doing everything the way you're doing things now, what can you expect to have happen? This is often sort of the base case or reference case that we do in these types of analyses. And this becomes a very useful way to, first of all, get people thinking about, okay, so what would a conservation future look like? What would a development future look like? What would, whatever the scenarios we want to articulate look like? Gets them thinking, okay, well, so what about land use? And what do we think about that? And what are the trade-offs? And, you begin to ask questions like that. As we look at things like water policy, institutions like the water rights framework in Western water law, if we wanted to make changes to those that might set us off on a different trajectory, how would we represent that, and how would we actually model that change, and have some sort of sense about how that landscape is doing at producing the stuff we care about collectively as society. In this case, we also did an 1850 analysis. The Willamette is a cool place to do science because there's just been tons of science done here around the river. And there's a lot of interest in the turnout tonight is a good example of this. But one of the things that was done was back in the 1850s, the General Land Office did surveys across the Willamette where they had folks coming in and marching along and writing down what they saw at transects across the river, going from Portland down to the headwaters above Eugene. And because those written records exist, it's possible to reconstruct what that landscape looked like. This was some work that was done by the Oregon Natural Heritage Program, I think. Dennis, is that right? Yeah. And the Nature Conservancy to look at those general land survey records. And it was like, as I'm looking across the transect, like here, I'm seeing 100 feet of open land, and then there's a riparian forest that's ash-dominated, and then this, and this as you move across these transcripts. So you get a pretty good sense of what the landscape looks like, and so it's been possible to reconstruct what we think the landscape looked like based on these GeoL survey records. This was done as part of this previous effort. A couple things to notice here. First of all, a very complex channel. You can see lots of sub-channels here, lots of riparian habitat, lots of complexity in the river. The other thing you notice is up along the top here, looks like there we go. Pay attention to this up here. We're going to look at a couple slides under this, an equivalent version of this in current conditions and then future conditions as well. But this is this is a pretty sparse set of trees up here. These are as a result of burning in the valley. In 1850, there was regular burns that the Native Americans subjected the valley to on a regular basis. That had very strong implications on ecosystems. Here's what it looked like in 1995. Pretty different. There's that. You notice a lot more Doug fir up here along the ridge lines. This is, just to locate you a little bit, this is just north of Eugene Springfield area, sort of looking over at the Coburg Hills in the background to help orient you a little bit. Should have put up a locator slide on this. But much more wood, much more Doug fir up in the foothills there. Direct result of not burning. Doug fir are not a fire-tolerant species, and so when there was burning on a regular basis, it kept that area thin. It preserved the sort of oak savanna ecosystems that were once a dominant ecosystem in the Willamette Valley. Those oak savanna ecosystems are pretty well gone at this point. They're not completely gone, but they're down to small percentages of their historic range, largely because of a change in fire regime. But the other real big obvious thing here is the channel is much simpler because we're good at putting revetments on rivers and stabilizing rivers. We got that one figured out quite well. So that has big impacts. The other thing that's obvious here is very well developed riparian forests. These were in areas that weren't fire prone because they were too moist. You had nice riparian forests in here, great for ecological production, but if you're raising crops, you don't want those. You want that. These are very fertile lands because these are the bottomlands that tend to flood on a regular basis and tend to be quite good soils and nutrient rich as a result of that, particularly for growing things like grass seed that are pretty tolerant of slightly wet soils. So this is 1995. If we jump ahead to 2050, and I think this is a planned trend scenario, you see you get a sense of sort of what we try to do here. So what this process was about was, okay, we know we've got a bunch more people coming into the landscape. So where do they go? Well, where they go depends on a lot of things, not the least of which is what's the nature of the land use planning system. If we're under sort of status quo situations where we have a robust land use planning system that really pretty severely restricts development in rural lands, then those people, to take X number of people and to pack them into the landscape, if you don't put them in the rural lands, they got to go someplace else. It's like a balloon that you squeeze, and it either pops out here or pops out here or something. But those people have to go someplace. This example of the conservation scenario, same number of people coming into the landscape, but you'll notice a few things. Gets a little bit sparser up here because part of the conservation scenario include sort of active restoration of oak savanna ecosystems, the introduction of fire, et cetera, reintroduction of fire. You see a pretty protected rural landscape here. It's not a whole lot of new development in the rural landscape under conservation scenario. The assumptions that went into the models that produced this scenario said, okay, we have limited capacity in resource lands to populate these lands under robust resource land protections policies. Those people ended up in Eugene and Springfield or Portland or wherever the case might be, and one of the consequences of that is, is a particular pattern that we see on the landscape here. And then just to compare that back to the original, even under our most conservation-oriented scenario, and this was pretty aggressive conservation restoration, we still see a pretty impacted river. So I'm just going to go through all these one more time. 1850. This is, let's see. Not sure what's going on. That's current conditions. This should actually be the development scenario. You see, development scenario, we assume that land use planning was relaxed, that economic forces sort of drove the development of resource lands. So you see, it's a little hard to see here, but you can see the sort of speckling of residential construction throughout. That's a consequence of that. That is a modelable thing. Also notice a lot more trees up here because we didn't really try to do conservation stuff up there. Conservation scenario looks pretty different. This stuff that we do as people, occupying the landscape, it makes a difference. And if you look at a slice of the landscape from, let's say, 2000 to now, let's say a 10 to 12 year window, you see relatively little. But when you start looking over larger and larger time frames, let's say out to 2050 or out to 2100, you really begin to get a sense that, okay, these decisions that we make now, they really do have a consequence. And as a scientist, I bring no intrinsic value to whether one landscape is good or another landscape is bad. The role of science in this alternative futures process is to work with stakeholders to identify what are the dials and knobs that we can turn, play those out to the best of our ability in a very unbiased way, and then let the stakeholders chew on that stuff and make their own decisions about what they value, what the trade-offs are, what the right sort of trade-off is, and go from there. But it's a really nice blend of doing what we consider to be good state-of-the-art science, but doing that in a way that is not guiding policies, or at least not suggesting policy, but at least allowing policymakers to understand consequences in ways that they can have more informed choices. That's really what this stuff is all about. Okay. So here's a good example. This came from the previous work as well. So what we see here is across the bottom is how did we do at producing stuff in 1850? How did we do under the conservation scenario in 2050? How do we do under the planned trend scenario in 2050? How do we do in the development scenario and plan in 2050 against some things that we know people care about because we've asked people, what do you care about? And this has been some of the response. It's not been all the response, but it's been some of the response. And so this is percent change relative to 1990. And so big numbers down here on things like native terrestrial habitat means we've lost, from 1850 to now, we've lost pretty significant chunks of habitat. We're running at about 40% of where we were in pre-European settlement, 1850. But that's not the end of the story. There are things that we can do, and this is where all this work going into doing the best job we can of projecting these future scenarios, you start to see some of the consequences of. Well, also under this conservation scenario in this case, where we adopted decisions, policies, strategies, et cetera, that were really focused on protecting the resource, you can restore a lot of function compared to current conditions. And this all assumes about twice as many people in the landscape. Pretty close to double number of people landscape. What you do around conservation, in fact, if you believe the models, which I don't, but I believe it more than anything else. Sort of like you got. No, we won't go there. Never mind. I'll talk about that more in a little bit, maybe. But the point here is, for at least this set of indicators, it makes an impact what decisions we make now and over the next 40 years, in this case, on how well we think that landscape can actually do at producing that. And conversely, for some of these other things, we can lose function as well with the same landscape, same number of people, different choices about how that landscape is managed. It does have an effect. This is one list. We could come up with a different list. And again, the idea is, as we project these future landscapes, to the degree that we can reflect how those landscapes are doing at producing stuff that people care about. In this case, it's mostly ecosystem stuff, but this list could just as easily have been jobs, or or economic development, or any metric that we can compute on these current and future landscapes. That gives us some ability to say, okay, well, so if I'm a policymaker and I don't care squat about this stuff, and the other trade-off analysis gives me something else I really care about, then that's a set of choices that I might want to look at. Or if I really care about this stuff, then I would probably want to discourage choices that were more down here and encourage choices that were more in this category. Yeah. Yeah, a very good point. And that observation is right on. As we got higher flashiness in the system, we got more water coming down in these winter events. One potential approach is to build more dams or raise the elevation of dams. Both of those are very expensive options, and there's other side effects, but they're options. They're not the only option. The other thing we could do is start to add complexity to the river and provide some floodplain storage for that water to accomplish a similar goal. What's the relative effect of that? And I can't stand here today and say I know the answer to that, but I can stand here and say the reason we're doing this study is to set up this framework so that we can play those two scenarios out, express it in terms like this, whatever the list of metrics are, and we really rely on stakeholders to identify the set of metrics that are of importance, and begin to play those out in this sort of scenario analysis type of thing. That's why we're in the midst of this similar effort, building on this one, but much more focused on water. Yeah. No, that's a really good one. One of the slides I took out but almost had in here was the amount of endocrine disruptors and other hormones that are in the water system. It turns out there's about 600 pounds a year that are added to the Willamette, so it's already there. How effective it is, I don't know. But what I will say is one of the things we can do very easily once we get the scenario machinery set up is say, okay, let's run this with a assumption that we're going to double in population, but then let's run it with an assumption that we're going to double, that's going to take us 100 years to double instead of 50, or something like that, and begin to, again, go through this analysis and say, okay, what are the consequences of that, for better or worse, against a set of metrics that stakeholders tell us they care about. That becomes one of the, again, I use the term dials and knobs, that we can potentially turn in this system and play out that scenario and then make some sort of assessment. But you really have to do that within the context of all this other stuff that's going on. So it becomes quite difficult to talk about one thing. It really, why we talk about things like conservation versus development scenarios, is we package a bunch of those things together that are sort of logically coherent, and those become a scenario that we then play out, and we can sort of fine-tune that to look at specific policies, but it's a very large search space to do that across the range of possible decisions that are available to people throughout the Willamette. Sure, really good question. And temperature is a big issue in the Willamette, as most of you are probably aware. What's that? Oh, repeat the question? Sure. I will. Let me take a stab at it. If I screw it up too badly, let me know. The question was, as we look at potential warming effects over the next 20, 30, 40, 100 years, and their adverse impacts on cold water fish, and at the same time we've got wastewater treatment plants that are dumping warm water in the system, and some of you are probably familiar with this. There's a lot of interest in the state in looking at mitigating heat loads into stream systems from municipal wastewater treatment plants. They turn out to be the largest single source of heat in the Willamette, outside of, well, anthropogenic sources of heat at least. Does it make sense to focus on wastewater treatment plants when we got this background signal of climate change that may make the whole conversation moot? Is that a fair summary of the question? Okay, sounds good. Well, so the answer is, this is my standard answer. I don't know, but the reasons we do these things is so we can answer questions like that. So one of the things that we'll get out of this study at the end of the study, and we're not going to get there before 7:20 or so, is that that's a really good example, again, of the type of scenario that we would like to be able to play out. If we do that with best available science and best available models, we can begin to partition out the heat load contributions. And in fact, this is part of this effort that we're just getting started on right now. It's the temperature profile of streams under current temperature and flow, and other sorts of modifications that involve twice as many people sucking out of the Willamette while we're continuing presumably to maintain ag and other uses of that water, becomes a really good example of the sort of thing that we would be able to explore. So I don't have an answer for you right now. Ask me again in 3 years, and I can probably give you a pretty good answer that's going to be the best available answer we've got based on best available science. But it's a really good question. Really good question. Yeah. Okay, so I'm getting signaled here. I'm going to skip through a couple of things really quickly, focus on just a couple slides here, and do I have 5 more minutes, Nick? 15 total. Okay, sounds good. I'll try to finish up by 20 after, and we'll leave a couple of minutes for questions. So we did get this project funded, and it's pretty cool. NSF introduced a new competition last year called Water, Sustainability, and Climate. It was really to look at sort of the nexus of those three issues. OSU competed for that. Extremely competitive process. I think they funded about 4% of the proposals that were submitted. So we were fortunate to get funding for this effort. Although I have to say we did a nice job with the proposal. And they funded it. So we now have this study. It's about $4.3 million to study the nexus of climate, water, future change, the various uses for water that go along with that, and what we propose to do this within this alternative futures framework. NSF liked that. In fact, they fund a lot of this work over the years. And so we now have this project that we've been involved in about 1 year right now. It's a 5-year project, so we're still in the early phases of this effort. But these are the questions. Where are climate change and human activity most likely to create conditions of water scarcity? Well, good question. But at this point, we can't really even answer too effectively. The question is, which is more important, population growth or climate, in terms of impact A, B, or C? Well, there's not an obvious answer to that question when you think about it, but one of the reasons why we're doing this study is to begin to parse out those signals, look at the system as a whole, but then to begin to parse out these individual signals to get a sense of under what circumstances is climate the big driver, under what circumstances is population the driver. And there are other drivers too, but those are the two big ones. Where is water scarcity most likely to exert the greatest impact on ecosystems and communities? Really interesting question. We don't have answers yet, but we're assembling the pieces in place to do this. And then most importantly, what strategies would allow communities to prevent, mitigate, or adapt to scarcity? And again, one of the reasons we look at these alternative future scenarios frameworks is they allow us to play out different strategies and say, okay, well, this one worked pretty well. This one didn't work at all. This one worked under this circumstances, but it utterly failed under those circumstances, and begin to get a pretty good sense of what can we do to proactively try to mitigate some of these effects we see coming down the road from climate, population, or potentially some other factors as well. And it's all about scarcity. Scarcity is a really nice framework to think about this stuff in. Water in the West, well, we think of Oregon as a fairly wet place, but in this case, it's all about timing. If supply looks like this and demand looks like this, you're great over here. You're great over here. You got real problems in here, and so this is really the situation we're in. And we can put in dams, which shift these lines one way or another, or we can look at other ways of storing water, snowpack, etc., that shift these one way or the other. But the real problem is, what do you do right here, where your demand substantially exceeds your supply? Lots of ways to talk about scarcity. For the economists in the room, and I'm not one of them, here's how you might think about scarcity. You look at a demand supply curve, and you say, oh, well, as soon as we get up here to where we're pretty steep on this, we're scarce. And as long as we've got low prices, then we don't have scarcity, almost by definition. So this is one way to think about scarcity. Here's another way to think about scarcity. If you're a fish, you don't look at those marginal supply-demand curves. You say, okay, do I have some place where I can swim to reproduce? And so the definition from a sort of a biophysical point of view is very different. And one of the challenges we have in this project is just even getting our heads wrapped around scarcity, how we think about scarcity in economic terms, in other types of terms. We worked with stakeholders quite a bit and asked the question, how do you define scarcity? And we get a bunch of different answers that deal with things like, is the system reliable? Do we have sufficient water quality to support our needs? Do we run out of water at the end of summer? Are we at a place in the basin that actually has access to water as opposed to limited access to water rights? Do we have allocations for sort of those non-critical uses? And the general answer we get is things like there's not enough affordable, attainable, and dependable clean water when and where it is wanted or needed by humans, animals, and plants currently into the future. Well, that's a pretty good definition, but yet another definition of scarcity. So one of the things we're doing is really trying to get our heads wrapped around several useful definitions of scarcity that become part of the language that we use to talk about this stuff. I think I'm going to stop there. You're probably wondering what this slide is, so maybe I'll just finish by explaining this slide. When we write these proposals, one of the things I like to do at the end of the day is run them through Wordle, which is this website where you feed text in, and it comes back with graphical representations of the words that were in that proposal, where the size is related to how often that word shows up. Okay, you got that? Everybody follow that? I don't think I can say that again. So this is what our proposal looked like, and I was sort of pleased with this because it really captured what this proposal is about in a lot of ways. First and foremost, it's about water. And that shows up because water shows up lots of times in this proposal. It's also pretty, you see this term Envision show up here. Envision is this tool that maybe I can come another time and talk about, but it's a tool we've been developing for about 15 years now, 10 or 15 years, that does these alternative futures analyses. And it's a pretty cool tool. If anybody's interested, talk to me afterwards. But it's basically a quite robust modeling tool that allows us to do these alternative future projections and assessments that go along with those projections. But a whole bunch of other stuff shows up here as well. Climate, river, scarcity, economics, social economics, population, hydrology, alternative policies. I like this one, help. That's sort of how I feel. That's sort of how I feel when I'm thinking about this stuff. Change shows up pretty prominently. Ecological stuff shows up pretty commonly, but so does use. Water use is an important piece of this. Looking at the future. This is a nice way to sort of capture sort of the breadth of this proposal in that it really is focused on bringing together biophysical science, so we understand we got extremely good hydrologists that are involved in this effort that are modeling the hydrologic system in the valley, both from the supply side and the demand side. We've got a very good group of economists that are involved in this proposal that are doing economic assessments and also bringing an economic perspective on how people make decisions and incorporating that into this modeling framework. We've got this amazing breadth of disciplines represented in this project, because to look at the system holistically, you got to have that, or you miss stuff. So we have social scientists economists, plant people, planners, like I said, hydrologists and folks who really look at things like aquifer storage and recharge systems. One of the other technologies as an alternative to dams that we might look at that may or may not be a more or less expensive way to manage the storage issue. But this really summarizes what this proposal is about in a lot of ways, but it's really that interdisciplinary perspective that both makes this very cool. It's a very cool project, very challenging project, but also fairly unique. We as a scientific community are really just figuring out how to do this stuff. And it's a different paradigm for how we think about doing science. It's a very interesting and useful paradigm, we think. And with that, I'll close. And if there's time for questions, we'll do questions.
Well done. Thank you. We're going to have John back here in about 3 years. I think you said 3 years. You'll have answers from Mike, and so we'll bring Mike and John back and see how we get going. So let's start back here with Dave. We'll repeat the question too.
Mm-hmm. Yep. Mm-hmm. 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 Yep. Yep. Well, so a couple of responses. For the most part, I try to stay out of the political conversations because I view my role of science to be an unbiased provider of information. Oh, yeah, sorry. Should we rephrase that real quickly? You want me to take a stab? Okay. Correct me if I get too far off the rails here. The question was, how do you bring this stuff into the political conversations, and particularly the political conversations that are going on in Corvallis right now about things like annexation, about things like riparian development or alternative treatment systems that involve wetlands, et cetera. I'll do my best, but I'm not going to do very good on this one, I don't think. Because, again, I don't view my role as science to advocate for a position. It's to provide unbiased information. The other thing I would say, though, is one of the things that we're doing with this project is this pretty rich stakeholder engagement process, of which Linda Modrell, who was sitting over there just a minute ago, still is, okay. She's working on it. It's a good example. Many of you probably know Linda. She's one of our county commissioners. Linda is involved quite heavily in this project, providing both input into how city governments and county governments look at some of this stuff, as well as we talk about this being a two-way knowledge street. So we learn from her, and she learns from us and brings back that to, presumably she brings back to her conversations. That's one way to do it. In the specific case of a decision Corvallis is looking at next year, my guess is it's going to be pretty tough to bring much of this to that conversation because we're really still in the getting it off the ground stage. If you said 3 years from now, I'd have a different answer for you. Oh, absolutely. Absolutely. That's the reason for being for Envision, is to allow us to articulate and capture policies, put them in this mix of models of change that involve both human-based change, anthropogenic change, as well as more biophysical types of change processes, and do that in a way that's extremely policy relevant. That's the whole reason for being. Absolutely. There's a whole bunch of other issues that go along with that. These aren't studies you do overnight. There's a reason we wanted $5 million to do this. But that said, this is very much geared with those sort of processes in mind. And in fact, we've worked with quite a few communities around the Northwest to do just those types of visioning processes in the past.
Leo?
Hopefully this will be an easy one. You use the term headwaters. Is there a specific lake or a specific geographic region that you would say this is a headwaters or Willamette is more common?
No, that's fair to say. It's not a place. It's a, you look around the rim of the Willamette Basin, and all those what we refer to as first order streams are headwater streams at some point or another. They start from nothing and end up intersecting the Willamette downstream. So it's really the sort of band around the edge that constitutes headwater streams. I didn't show this, but I could show you a representation of the stream system we're using that consists of about 10,000 individual street segments that go from the mouth of the Willamette all the way up quite high into the headwaters to the first order streams, and we're modeling that entire system in this effort. It's a pretty ambitious modeling effort. In fact, it's one of the most comprehensive looks at hydrologic modeling that has been done to date. Still very much in that process, but our definition of headwaters is the first order streams in this stream network.
Other questions? Yep, back here.
All right. That's certainly a very important question. No disagreement with that. I would also say that focusing exclusively on agriculture, it's 50% right now, but that leaves 50% in other uses, and this is a tough problem we're looking at. If you really put your thinking cap on and looking 50 years down the road, doubling the population with really less available water when you figure in climate impacts, it's a serious problem. So looking at one single piece, I guess I would be a little bit cautious about. Clearly, the ag piece is an important piece, but it's not the only piece. There's a bunch of other pieces that are important and becoming more so as we look at a doubling of population. That 15% domestic, in the absence of any other change, all of a sudden now starts to look more like 30% domestic. So that's a piece we can't ignore either.
Yep, good question. Other questions out there? Right down front.
Yeah, so the question was, are we looking at various conservation measures as part of the strategy mix that we look at when we model the futures? The answer is absolutely yes. The water demand side of the equation here is very important to us, so we're looking at that in quite a bit of detail. And conservation is very clearly part of that. At least it will be under some scenarios. And I think one of the things we'll do with these scenarios is look at conservation practices that are quite aggressive versus conservation practices that are less aggressive, and begin to get a sense of, well, how much difference does that make when you look at the overall picture?
Other questions? I've got one quick one for you, maybe it's quick.
Sure.
The relative importance of in-stream uses. We've seen them grow in importance as we've recognized the importance of habitat for native fish, for salmon in particular. And the binding effect that knowing that we've got discharges going into those rivers, whether it's causing heat or it's causing changes in chemical balance, or we simply need a minimum flow to maintain those species. Are you projecting the possibility that if we want to maintain a healthy habitat for those 60 or 30 native species, 60 species in the river, that we're going to be finding our uses of the river, and wastewater discharge is a big use, constrained in the future, perhaps a real pinching point, rather than the consumption of water, our ability to dump more water in because we're adding heat and all those other things.
Oh, absolutely. That's a really important part, and every time we talk to stakeholders, that's part of the conversations that we have is these are the uses that are important to us, and that includes in-stream uses for fish. There's real limits on what the possibilities are there. It's a small number right now. When you look at the in-stream rights for environmental flows compared to all the other rights, they're tiny. They're also very junior rights for the most part. So those are tough ones to acquire under the current institutions around water rights and Western water law. One of the things we are talking about doing, and we haven't really figured this out completely yet, is looking at a scenario that changes the institutions around water allocation away from the sort of Western law, water law, prior doctrine of prior appropriations, and look at some other potential models for how that sort of institutional constraint on water might play out, and see if that gives us anything or not, or what the trade-offs are that are associated with that. We're still early in the conversations around that in terms of how we deal with that, but this connection between hydrology, temperature, various uses, supply, and impacts on fish is very much a really important dimension of this work.
Thanks. Thanks. Yeah.
So on a techie side, when you're developing your model, are you developing it in fragments with different teams putting stuff together about water quality, about rainwater, about climate change? And trying to bring them together, or are you have a broader look?
No, I'm going to give you a short answer to what I'm going to have a hard time making a short answer. The short version of it is Envision was designed from the ground up to be this integrating tool that allows you to put in representations of different processes and have all those processes coexist peacefully and, in fact, play out in parallel as we run together. There's a really interesting software architecture piece of this that I'm not going to make you suffer through at all. But it's pretty cool, and it's also quite robust. It's we're approaching 1 million lines of code to support all this work at this point. So it really is focused on this integrated piece that allows individual components to be developed by individual teams to the best of their science, understanding of science, and then Envision becomes a tool where you plug these things in and it plays them all out in parallel together. It's pretty cool. And I'll leave it at that. If you want more details, glad to provide more details after the talk.
Okay. Thank you, John.
Okay.
So be here next month on